Okay.
So I think we can start. So
Okay.
it's my great pleasure to introduce Ioannis Dokas from National and Kapodistrian University of Athens, who will talk about Quillen-Barr-Beck cohomology for restricted Lie algebras. Okay, you can start, Ioannis.
Thank you. First of all, I would like to thank the organizer for the invitation. And it's a big pleasure for me to give a talk in this seminar. As you see, the title of the talk is Quillen-Barr-Beck cohomology for restricted Lie algebras. And this talk will be based... there's something wrong here. Sorry about that. Okay, okay. We'll go like this. It doesn't work there. Okay. And I'm sorry for this technical problem. The talk will be based in these two articles. So proofs, details, and reference can be found in these two articles. The plan of the talk is as follows. First, I will talk about restricted Lie algebras and give the necessary background for Hochschild cohomology in order to define Hochschild cohomology. Then speak about Quillen-Barr-Beck cohomology and define Quillen-Barr-Beck cohomology for restricted Lie algebras. Next, speak about torsors cohomology, give some elements from this theory, and speak about twofold extensions of restricted Lie algebras. And finally, establish an A-term exact sequence for the Quillen-Barr-Beck cohomology of restricted Lie algebras. So let me start with the definition of, I don't know, can you see the slides? Okay.
Now it's blank.
Yes.
Okay. I will start with the definition of what is a restricted Lie algebra. This definition has been given by Jacobson. So we consider first a field, let's say K, of prime characteristic P. Restricted Lie algebra is a Lie algebra L over K, together with a map which is called P map from L to L, which I will denote with this formal P power, such that the following relations hold. Okay, first relation is this one. The second relation is this one. And the last relation is this one, where I have to define what are these SI of X and Y. So the I SI of X and Y is the coefficient of lambda to the power I minus 1 in the formal P minus 1 fold product that you see here. To have an idea about this SI, if you are in a field of characteristic 2, then S1 of X and Y is just a bracket. If you work in a field of characteristic 3, then you have these formulas that you see here. And in general, you have the following remark. If H is the Lie algebra generated by the elements X and Y, then the SI of X and Y belongs to H to the power P, where P is the characteristic of the field, and H to the power N denotes, as you see here, descending central series. Then there is, of course, a notion of morphism. So let me write this. So Lie algebra homomorphism F from L to L prime is called restricted if the map commutes with the formal commutes with a P map, and I will denote by Rli the category of restricted Lie algebras over K. Next, I will need the notion of restricted Lie subalgebra. So a subalgebra H of L is called restricted if it's closed for the P map, as you see here. The next thing I would like to mention is abelian restricted Lie algebras. So if the bracket is 0, then from the previous definition, somebody can see that an abelian restricted Lie algebra is just pairs like this, V, F, where V is a K vector space, and F is a map from V to V, which is P semilinear. That means that you have these two relations. Now, next, I have to give examples because maybe this seems a bit artificial. So let me give examples and see how this structure appears in a natural way. And the first and the prototype example of restricted Lie algebra comes from associative algebras, and it follows in particular from a theorem of Jacobson, which is the following. If you start with U, an unassociative algebra over K, and K is a field of prime characteristic, then you can consider the induced Lie algebra, which has the bracket, the commutator, as you see here. Now, this induced Lie algebra, together with the Frobenius map, is a restricted Lie algebra. So let me recall that the Frobenius map is a map which associates to x to the power p, where p is the characteristic of the field. So that means that the Frobenius verifies all the relations we've seen in the definition of the restricted Lie algebra. And in this way, it's defined a functor from the category of associative algebras over K to the category of restricted Lie algebras. From this example, from this theorem, it follows a very big amount of examples, because since you have an associative algebra over a field of prime characteristic, then you know that the induced Lie algebra is a restricted Lie algebra equipped with a Frobenius as a P-map. And of course, it follows that the Lie algebra of matrices is a restricted Lie algebra, and also someone can prove that the spatial linear Lie algebra is again a restricted Lie algebra. The next example, which I would like to give, is derivations. Comes from derivations. So if we start with B, a K algebra, not necessarily an associative algebra, then we can consider the set of K derivations of B. And this set, we know that is endowed with the structure of a Lie algebra, where the Lie bracket is given by this formula. Now, if we are in a field of prime characteristic, and we take D a derivation, we can see that D to the power P, where P is the characteristic of the field, is again a derivation. And this follows from Leibniz formula, which you can see here. So as you see in this formula, you have these binomial coefficients, which are 0 in characteristic P, when I is between 1 and P minus 1. And from this formula follows that D to the power P is a derivation. And therefore, the set of K derivations of B is a restricted Lie algebra. The next example, which is related to this one, comes from the theory of algebraic groups. So if you start with G being a fine algebraic group over K, then the associated Lie algebra, somebody can prove that the associated Lie algebra of G is actually a restricted Lie algebra. And the next example comes from the theory of Hopf algebras. So the notion of restricted Lie algebra appears in prime characteristic in structure theorems of Hopf algebras, like, for example, Milnor-Moore type theorems. And this is because the primitive elements of a Hopf algebra is a restricted Lie algebra. And next, the last example which I would like to give is from the theory of fields, field theory. So here, in the theory of Jacobson-Galois correspondence of purely inseparable extensions of exponent 1, the Galois groups of field automorphisms are replaced by restricted Lie algebra of derivations. So somebody can see from these examples that the notion of restricted Lie algebra appears naturally in prime characteristic in different fields. Next, I would need the notion of free restricted Lie algebras. So because I would need the free functor in order to define cohomology. So we'll start, let's say X is a set. You can consider the free associative algebra on X, T of X. Then the free restricted Lie algebra on X is a restricted, is the restricted Lie subalgebra of the induced restricted Lie algebra of the free associative algebra on X generated by X. So in other words, as a K subspace of T of X, the free restricted Lie algebra generated by X is generated by p to the nth powers of Lie polynomials. And in this way, is defined a functor from the category of sets to the category of restricted Lie algebras, the free functor, which of course is left adjoint to the forgetful functor, the functor which takes a restricted Lie algebra and forgets the structure, and you get a set. Now, let me try to give the connection with the theory of algebraic operats. So a good reference for this is the book of Lodé-Valette on algebraic operats. So there you can find more details. I will briefly describe how we recover the notion of restricted Lie algebra in the theory of algebraic operats. So I'll suppose that we denote by vect the category of vector space over a field, and we have P, a reduced algebraic operat. Then is defined a monad SP by this formula in the category of vector spaces that you see here. Now, an algebra over an operat, P, is an algebra over this monad. So that's the definition. P algebra is defined as an algebra over the monad SP that we see here by this formula. Now, somebody can notice that if you take P to be the associative operat, then this formula gives you the tensor algebra on V. So somebody can realize that from that you get the notion of associative algebra. So you have that if P is an associative operat, is the associative operat, then you get associative algebras through this definition. Also, if you take the commutative operat, then here you get the symmetric algebra, and you get the commutative algebras. And also you can prove that if P is the Lie operat, then you get Lie algebras. So this is the way to recover all the classical algebraic structures with the theory of operats. Now, if we work in characteristic P, then there is this notion of divided powers of algebras over an operat. And it was Benoit Fraisse who defined this notion. So suppose, suppose that we have a field of prime characteristic. It was Benoit Fraisse who considered the monad gamma P that you see here, defined by this formula. Now, if you compare with the previous slides, you will see that here we take invariance instead of co-invariance. Somebody can prove that this is a monad in the category of vector spaces and define an algebra with divided powers over an operat P as an algebra over the monad gamma P that we have here. Now, the first examples are the following. If you take P to be a commutative operat, then you get what we call a gamma algebra, which is nothing else than a divided powers algebra, or a commutative algebra with divided powers. So this is a commutative algebra equipped with operations. And let me mention that this notion of commutative algebra with divided powers was introduced by Cartan in his study of homotopy of simplicial commutative algebras. Also, this notion has been studied by Roby, and I know that this structure a tool in crystalline cohomology theory. Now, if we take P to be the Lie operat, then there is a theorem from Benoit Fraisse who proved that a gamma Lie algebra is nothing else than a restricted Lie algebra. So this is the way that we recover the notion of restricted Lie algebra, which has been defined by Jacobson through the theory of algebraic operats. there are other examples with the Poisson operand, etc. So this is what I would like just to say about this connection. And next, okay, we have a remark that in characteristic 0, gamma p algebra does not carry more structure than SP algebra, because there is an isomorphism between these two, the norm isomorphism. So in characteristic 0, we don't differentiate them. There is no more structure. So that's interesting in characteristic P. And now let me recall some background which we will need in order to define Hochschild cohomology. There is a notion of restricted enveloping algebra and a notion of restricted module. So if we start with L being a restricted Lie algebra, we can consider the enveloping algebra of L, which I denote with this capital U. And the restricted enveloping algebra of L is defined as a quotient of the enveloping algebra by the ideal which is generated by elements of this form. So basically, we identify the formal P map that we have here with the Frobenius which exists in enveloping algebra. And there is a notion of restricted module, which would be a Lie module, L Lie module, such that this relation here holds. And of course, somebody can prove that the category of restricted L modules is equivalent to the category of modules over the restricted developing algebra. And in this way, we have defined a functor, which I write like this, from the category of restricted Lie algebras to the category of associative algebras. And we associate to restricted Lie algebra L the restricted developing algebra of L. And this functor, it's left adjoint to the functor that we have mentioned in Jacobson's theorem at the beginning of the talk. Also, let me add that we have a Poincaré-Birkovit theorem for the restricted enveloping algebra, analog to the one which exists for the enveloping algebra. And also, there is an injection of L to the restricted enveloping algebra of L. Now, I think we are ready to define Hochschild cohomology and speak about extensions of restricted Lie algebras. So it was Hochschild who defined cohomology for the category of restricted Lie algebras in completely analogy with the case of Lie algebras. So for the cohomology are used Ext functors, and for homology Tor functors. Now the role of enveloping algebra now is played from the restricted enveloping algebra, and we have the following formula, which gives the Hochschild cohomology. As you see here, we have restricted enveloping algebra instead of the enveloping algebra. As for the coefficients for this cohomology theory, we have restricted left L modules. Now, let me pass to extensions. So its cohomology theory is related with the notion of extension. So a short exact sequence of restricted Lie algebras like this is called an abelian P extension if the kernel here is abelian. If additionally the P map on the kernel is 0, then if we have this condition additionally, then the above extension is called a strongly abelian extension. And now we have the following observation that the Hochschild cohomology classifies strongly abelian P extensions. So, particularly, the second Hochschild cohomology group classifies strongly abelian P extensions. And this remark has been for me the motivation to study cohomology for the category of restricted Lie algebras. Because it arises naturally a question, can we define cohomology, which classifies general abelian P extensions and n-fold extensions of restricted Lie algebras. That was my motivation to study this subject. And in this way, I was led to read the Quillen theory for universal algebras and Barr-Beck cohomology theories. So let me give some elements from Quillen-Barr-Beck cohomology theory. For Quillen's cohomology, there is the book Homotopical Algebra, and also the famous paper on cohomology of commutative rings. And for cotype cohomology, there are papers from Barr and Beck. So let me give the background for the definition of Quillen-Barr-Beck cohomology. So we start with E being an algebraic category. So we can imagine associative algebras, Lie algebras, restricted Lie algebras, etc. Then we have to define Beck modules. And the name is after Beck because Beck was in his thesis tried to answer to the question, what should be the right notion of coefficients for a cohomology theory? He considered this notion of module, which now we call Beck module. So let me give the definition of a Beck module. What's a Beck module? So if you start with an object X in your algebraic category, then you can consider the slice category. That's a category of objects over X. And you can consider abelian group objects in the slice category. So a Beck module over X is an abelian group object in the slice category. We will denote Beck modules over X with this notation that you see here. In this way, we see that there is a forgetful factor from the category of abelian group objects in the slice category to the slice category. And this forgetful factor, under the hypothesis that your E is a quite nice category, an algebraic category, admits a left adjoint. So there is a factor from the slice category to the category of abelian group objects, the slice category. And this factor is called the abelianization factor. So we'll need this factor in order to define cohomology. Next, there is this notion of Beck derivations. Again, the name is Beck derivations because it was Beck who tried to give an answer to the question. He gave an answer to the question, what should be the notion of that derivation? So Beck considered the following set. If you take an object Y in the slice category and M a Beck X module, then you can consider the following set that you see here with this formula. And this set is an abelian group because M is a Beck X module, which means it's an abelian group object. So this set has the structure of an abelian group. And this abelian group is called the group of Beck derivations of Y by M. Now, of course, is defined factor, contravariant factor for an X Beck module M that you see here from this definition of Beck derivations. Now that we have this contravariant factor, we can define Quillen-Barr-Beck cohomology groups as follows. First, the setup is that we are in a monadic category over sets. This is the case with our algebraic categories. We had, for example, seen that for the restricted Lie algebras, we have a free functor, but also in other cases, Lie algebras, associative algebras, groups, etc. So we have a monadic category over sets. Therefore, there is an adjoint pair of functors. F is the free functor from sets to E, and U corresponds to the forgetful functor. And now, if you have an adjoint pair like this, then you can associate to this adjoint pair a cotriple, which is this one, G, which is the composition FU. So that means an Edo functor in the category E. We call also this comonad, together with natural transformations such that some properties are verified. But what we have to keep in mind is that once you have an adjoint pair like this, then you can associate a cotriple. And now let me define the groups. So X is an object in the category, M is a Beck X module. Then Quillen-Barr-Beck cohomology is defined by this formula that you see here, which I will explain a little bit more. So we have an object X in our category. Then we consider using this cotriple, a cotriple resolution of X. That means a simplicial object over X. And then we apply the Beck derivation contravariant functor that we have seen just before, and we obtain a co-simplicial object in the category of abelian groups. And then we take cohomology. This is the definition. Because of this fact that we can, in this case, is define a simplicial resolution of X using the cotriple, we call also these groups cotriple cohomology groups. This is the general definition. Let me give examples of these constructions. Let me start with examples. So the first example, it is a category of groups. So if E is the category of groups, and you take G to be a group, then you can prove that a Beck G module is just a module over the group algebra of G. Second example is the case of the category of associative algebras. And if you take A to be an associative algebra, then Beck A module is nothing else than AA by module. If you move to the category of commutative algebras, then somebody can prove that a Beck A module is nothing else than a left A module. And finally, if you consider the category of Lie algebras, then a Beck L module turns out to be a module over the enveloping algebra of L. So somebody who is familiar with the cohomology theories of these categories can see that Beck's definition of a module captures exactly all the classical notions of coefficients for the corresponding categories, the corresponding cohomology theories. It's a good definition. And also, if somebody works the definition of Beck derivations in these cases, he will see that the notion of Beck derivations coincide with the usual groups of derivations. So, with these examples, I think we have an idea of what is a Beck module. And also, I can mention that the Quillen-Barr-Beck cohomology for our first example here is just the ordinary cohomology of groups. There is just a shift in the notation, but we get the same groups if we take the second example, then Quillen-Barr-Beck cohomology gives Hochschild cohomology for associative algebras. Again, we have a shift in the notation. And okay, Quillen's theory for commutative algebras is the famous André-Quillen cohomology. And for the last example, which is an example of our interest because restricted Lie algebra is a Lie algebra, in this example, we get the usual Cartan-Eilenberg cohomology with shift by one in the notation. So the question now for us is what happens for the case of restricted Lie algebras? What happens when we apply these general ideas of Quillen-Barr-Beck cohomology to the case of restricted Lie algebras? We have natural questions. So the first question is, what would be the Beck-L module when L is a restricted Lie algebra? And a naive answer to this, it could be a module over the restricted enveloping algebra. By analogy with the case of Lie algebras, where we had a Beck-L module for Lie algebras is a module over the enveloping algebra. That's the first question. The second one is, what could be the group of Beck derivations? And finally, what would give the Quillen-Barr-Beck cohomology for the category of restricted Lie algebras? And again, here, somebody can expect naively that we will get a Hochschild cohomology for restricted Lie algebras, shifted by one in the notation, as it happens for the case of Lie algebras. So the next paragraph is Beck modules for restricted Lie algebras. So it turns out, and the proof of this statement can be found in the first paper, that Beck modules are not restricted L modules over the restricted enveloping algebra, but it's something richer, is pairs like this, A, F, where A is a restricted L module, and F is a map, a P-similar map from A to into its submodule of invariance. So we do not obtain what we would expect, and from that, study can understand that the coefficients of this Quillen-Barr-Beck cohomology theory are not the same with the Hochschild cohomology theory, and we have something different. Now, based on this characterization and this first theorem, we can give an equivalent characterization of the notion of a Beck-L module as a module over a certain ring, which is not the restricted enveloping algebra. It's another ring, which is denoted by WL here. And this ring, as a K-vector space, is the tensor product of the restricted enveloping algebra by this commutative, this polynomial ring. You have this relation here. And such that these canonical maps are algebra homomorphisms, and the multiplication in this ring verifies these two relations. So this construction follows from the previous theorem. So we are based on the previous theorem to consider this ring, and in this way, somebody can see that Beck-L modulus is equivalent to the category of WL modulus. Now, let me mention here that this WL ring, this construction, has been considered by Paragis in his cohomology, in his work on cohomology of restricted Lie algebras. But what we see here is that actually we recover this notion through the notion of a Beck-L module. So the axiomatic scheme of Quillen-Barr-Beck cohomology recovers this construction. Next, I will identify a WL module with an AF module like this, where A is a restricted module over L, and F is a P-similar map from A to its submodule of invariance. So this I will be free to identify these two characterizations. So that's for Beck modules in the category of restricted Lie algebras. And now, if we take the definition of Beck derivation, then we end up with the following result. Again, the proof can be found in the first paper. So Beck derivations, as you see, who belong here. This Lie means they are it's in the context of Lie algebras, but the important thing is how this D behaves on an element like this, x to the formal power of p. Then we have this formula that you have here, and you notice that there is this term which is not in general 0, and this differentiates from the notion of restricted derivation. So now that we have the set of Beck derivations, we are ready to define Quillen-Barr-Beck cohomology for restricted Lie algebras following the general definition of Quillen-Barr-Beck. We will need this adjoint pair to find a cotripe resolution, but we have this because I described the free restricted Lie algebra functor. And we have an adjunction that I note like this, which gives rise to a cotripe in the category of restricted Lie algebras. And groups are defined by this formula. So again, let me recall, we take L a restricted Lie algebra, and we use the cotripe to define a cotripe resolution of L. This is a simplicial object over L. Then we apply the derivation factor that we have just we have just found. We obtain a cosimplicial object in the category of abelian groups, and then we take cohomology. So the question is, what kind of extensions are classified by this theory? And so that's the next paragraph. And I am ready to state the first theorem, which will give us a classification theorem for the first Quillen-Barr-Beck cohomology group. So the theorem is this one. It says that from the right hand here, we have the set of equivalent classes of abelian P extensions. So we see that this theory classifies general extensions. And in your left, you maybe notice here that we have this shift in the notation. We have one. Usually, it's the second cohomology group which classifies extensions. But in this theory, we see this shift in the dimension. As for the proof, details can be found in the first paper, but what we use here is the notion of the torsor. So what we prove is that this set of equivalent classes of abelian P extensions is in one-to-one correspondence with isomorphism classes of objects C in the slice the slice category, which are torsors for the Beck module AF. So this gives an answer, let's say, to the initial problem, and is connected with the initial motivation. Can we define cohomology in a way that we will classify general abelian P extensions? Now, if we want to give interpretations for the second, and even more, the second Quillen-Barr-Beck cohomology group, we are led to consider n torsors. And this is how I try to understand torsors cohomology and apply torsors cohomology theory to this particular case of restricted Lie algebras and obtain classification for two-term extensions. Let me briefly speak about this as well. Duskin-Glenn's torsors cohomology. This is the paragraph. It was Duskin who first defined the notion of an n-torsor. And actually, n-torsors is a simplicial interpretation of co-triple cohomology groups. And as I said, we'll use this theory to classify two-term extensions. Glenn was a student of Duskin, and he gave a generalization of this notion, and he developed this theory. Now, let me again briefly give the elements from this theory. For details, somebody can see the papers of Duskin and Glenn. So the context is, again, we work in a monadic category over sets. In this category, there is this adjoint pair of functors, which gives rise to a cotriple. There is a functor which is called n-truncated functor. I do not like this. So this functor takes a simplicial object in the category and truncates it at the level n. And this functor, we can prove that has a right adjoint, which is called Verdier coskeleton functor. In order to construct this coskeleton functor, we need the notion of simplicial kernel. Again, all this definition can be found in this in the papers of Duskin. Next, I will denote by this capital C this composition of these two functors, and we get a functor from simplicial objects of E to simplicial objects of E. First, we truncate, and then we construct a simplicial object with the coskeleton functor. So, if we have these definitions in mind, I can give the definition of the n-torsor without giving much details, but okay. So we take X, an object in our monadic category, and A, Beck X module, or in other words, an abelian group object in the slice category. Then a Kn torsor over X relative to U is an augmented simplicial object, as you see here, together with a morphism, chi, from Xn to A over X, such that some conditions are verified. So I will give these conditions without many details, but there are 4 conditions. The first one is that this augmented simplicial object is U-split. That means that the underlying object level there is a splitting. Then the next condition is that this chi here is a normalized cocycle. That means that these two relations hold. Next, we have that in the underlying object level, this commutative square actually is a pullback. And Kn minus 1 is a n minus 2 simplicial kernel. And the last condition says that the canonical map that we have from here to there to this object is an isomorphism. As I said, you can find details in the paper of Duskin. Now, there is a notion of morphism between n-torsors, and we have the category of n-torsors. Now, let me state the theorem of Duskin of interpretation of cotriple cohomology groups. So this is the theorem. As you see here on your left, we have this formula, the nth cotriple cohomology group of X with coefficients in a Beck X module A. And Duskin proved that the nth cotriple cohomology group is in one-to-one correspondence with the set of connected components of the category of n torsors, which we have just defined. We denote this category by this tors with exponent n. What we will use now this interpretation in order to classify two terms extensions in the category of restricted Lie algebras. In particular, we will study two torsors for the category of restricted Lie algebras. In order to do so, we will need the notion of crossed module. This notion exists for the case of Lie algebras, and it was Lode and Kassel who defined the notion of crossed module for the category of restricted Lie algebras. Now, we can define in a completely analog way crossed modules in the category of restricted Lie algebras as follows. So the definition is this. A crossed module in the category of restricted Lie algebras would be...
Excuse me.
Sorry?
May I ask a question?
Yeah.
Could you say why you're requiring the properties of n torsors, like condition 2, for example, as an alternative sum or something?
Sorry, the condition
to the n torsor, the slides that, yeah. So could you say a little bit about this normalized co-cycle? Why do you require this?
This is the definition. It's part of the definition. You need that in order to prove the theorem. I can give the details of the proof, but you can find them in the paper. At least for the case of two torsors, you can see how I used this condition. But this is the definition which I took from Duskin definition. There is an equivalent definition to this one by using the notion of I horns. I don't know if that makes equivalently. You have another description of n torsors. But
okay.
Yeah.
Thank you.
Yeah, at least for the case of two torsors, you can see how I use it for the case of restricted Lie algebras, but this is general.
Thanks.
Thank you for the question. So let me okay, crossed modules. I was here. Yeah, as I was saying, in order to study two torsors, I would need this notion of crossed modules. And I knew that exists in the category of Lie algebras, so we can define by analogy the notion of crossed module for the category of restricted Lie algebras. So that would be triples like this, where Mn are restricted Lie algebras, mu is a homomorphism of restricted Lie algebras. We have an action of n by derivations on M, so that's why there is this eta here. And such that these two conditions hold. So somebody who is familiar with this notion for Lie algebras, for example, he will realize that this is completely analogy. And what is important with that is that we prove, as for the case for Lie algebras, that the crossed modules is equivalent to the category of internal groupoids. And this we will use this result, which you can find the proof in the second paper I mentioned, which I mentioned at the beginning. This will be used when we will study the two torsors, and I will say where I use it. Now, let me speak about extensions, and in this case, we have twofold extensions. So for us would be a twofold extension is an exact sequence in the category of restricted Lie algebras like this, where mu is a crossed module in the category of restricted Lie algebras, the definition which we have just given. Now, once we have this notion, we can now state the second classification theorem. And this is related with the second Quillen-Barr-Beck cohomology group. What we can prove is the following. And again, here, the details of this proof can be found in the second paper. We prove that the set of equivalent classes of twofold extensions that we have in our right is in one-to-one correspondence with the set of connected components of the category of two torsors. And the proof now, as for the proof, as I said, details can be found in the paper, but I can say a little bit how this it works. We start with, let's say, a two torsor. We consider the Moore complex of these two torsors, and we prove actually that this is a twofold extension like this one, which we have just defined. And conversely, if we start with a twofold P extension, we use the result that crossed modules equivalent to internal groupoids. We associate an internal groupoid to this twofold extension. Then we apply the one co-skeleton factor, which I defined in previous slides, and we prove that we obtain a two torsor. So the definition that I gave. And so we verify that these four conditions are satisfied in the definition. And this is the sketch of the proof. And now, having this theorem and the Duskin's theorem, which gives us an interpretation of co-tribe cohomology groups through torsors, we can, as a corollary, state this classification theorem, which says that the second Quillen-Barr-Beck cohomology of L with coefficients at Beck L module is in one-to-one correspondence with the set of equivalent classes of twofold P extensions that we have just defined. And in this way, we give also this interpretation for two-term extensions. Now, next, what I would like to mention and finish this talk with this is the establishment of an 8-term exact sequence for the category of 8-term exact sequence for Quillen-Barr-Beck cohomology for the restricted Lie algebras. And I will start with a motivation from the case of Lie algebras. So it is known that if you start with an exact sequence like this in the category of Lie algebras, and you take A to be a left L module, then it is known that there is a 5-term exact sequence for Lie cohomology groups, for Lie algebra cohomology groups, and this is the 5-term exact sequence. Here, you notice you have derivations, then there is this term here, and then we have the second cohomology groups. Now, suppose that we start with a short exact sequence, an exact sequence now of, instead of Lie algebras, of restricted Lie algebras, like this. Then it is proved by Ekman and Stabak that there is a 5-term exact sequence analog to this one for now Hochschild cohomology of restricted Lie algebras. So the question now, which arises also naturally, is do we have something similar for Quillen-Barr-Beck cohomology for restricted Lie algebras? So that was my motivation. And the answer is yes. And this is based in a general result of Cegarra-Aznar. In particular, Cegarra-Aznar proved an 8-term exact sequence for torsors cohomology. And what I tried to see is what happens when I apply this to the category of restricted Lie algebras. So for the category of restricted Lie algebras, we can give an interpretation of the torsors cohomology groups which appears in this Cegarra-Aznar sequence. And in particular, I had to compute the 0 torsors cohomology and 1 torsors cohomology group of an epimorphism of restricted Lie algebras. And having also done the interpretations through extensions, we can prove a theorem where we have an exact sequence of 8 terms for the cohomology of Quillen-Barr-Beck for restricted Lie algebras. And we have this theorem. Again, these details can be found in the second paper. So what we have here is we have an exact sequence like this in the category of restricted Lie algebras. We note phi here, this epimorphism, and we take AF to be a WL module. Then we can prove the existence of this 8-term exact sequence that you see here. If you compare with the case of Lie algebras, here again we have derivations. These are Beck derivations. Here we realize that we have this term which is similar to the one which we had for the Lie algebras, and then we have these extension groups. As I said, for details you can see the proof, but what I have done is that if you take an epimorphism phi, then we have to give an interpretation of these groups that you see here, the 0 torsor cohomology for the epimorphism phi and the 1 torsor cohomology. These are constructions defined by Cegarra-Aznar, and in particular, we prove that the 0 torsor cohomology of the epimorphism phi is actually isomorphic to this term that we have here. Now, as a corollary of this result, using the interpretation of cohomology in terms of extensions, somebody can rewrite this result in this way. So we can get an 8-term exact sequence for Quillen-Barr-Beck cohomology. You notice here that we have 0 cohomology. This is the derivations. The Beck derivations is the 0 cohomology for cotriple for Quillen-Barr-Beck cohomology. So that's why we have this 0 cohomology here. And then we have the interpretations we use the theorems that we have just proved with the interpretation of extensions, and we get an 8-term exact sequence like this. So in this way, what we do, we replace the Ekman-Stabac 5-term exact sequence by this 8-term exact sequence in the context of Quillen-Barr-Beck cohomology theory. So basically, this was what I would like to present today.
Okay, so thank you, Ioannis, for this very nice talk.
Thank you. I don't know if I wrote fast. I don't know. Thank you very much.
I think it was very good. So there is, I think, let's see. I think there is a comment in the chat.
Okay.
Yeah, there is a question, I think. Can you read it?
Yeah. I think was. Thank you, Florin. So maybe I have to check this link, but UGLA structure with an option. We can define the Beck modules, if I understand, for a that would be possible to use the Beck module. Of course, the notion of Beck module is actually whenever you have an algebraic category, you can speak about Beck modules, and you will see that in the paper of Quillen, on cohomology of commutative rings, you will see it's the definition of an algebraic category. So and then you can construct the abelianization factor. Also, I can say for the case of the commutative algebras, this abelianization that I mentioned factor is related with the notion of Kähler differentials. If you are familiar with the Andrei-Quillen cohomology. But yeah, the answer is whenever you have an algebraic category, then you can define the notion of a Beck model. Actually, is the abelian group objects in the slice category. So we take an object, we consider the slice category. Let me remind this category has objects, morphisms, let's say y arrow to x, and you have, this is the objects, and then you have triangles as morphisms in this category. And you take abelian group objects in this category. So basically you have split extensions. That's why you see all this this structure in the kernel of such a split extension. As for the groups, is group algebra, etc.
Okay. Are there any other questions?
I can attempt a question.
Sure.
My interaction with sort of cohomology for restricted Lie algebras comes from like the algebraic group. If you take a reductive group, or let's just say a simple algebraic group, and then you take its Lie algebra, which you can also sort of identify with the Frobenius kernel, then you can get very, very explicit calculations of the Hochschild cohomology by kind of building up first from like the ordinary Lie algebra cohomology for just like the positive root spaces, and so you get these root sums that you can then inflate to from the ordinary cohomology to the restricted cohomology. You can then take the T fixed points to get it to then get the Borel cohomology, and then you can induce finally to get it all the way up to the whole restricted Lie algebra of the group. I'm just wondering if that sort of process of because you've got this 5-term exact sequence, which is very suggestive that you could do a similar thing in your category. Just wondered if you looked at any of that stuff.
Thank you very much for your comment. It's very, very, very interesting. I haven't looked to this. The only thing naively I have seen is that if you have the connection with algebraic groups it's very interesting. I haven't really looked on that. Thank you for this remark. What I can say is that we wrote a paper with Martin Frankland, Sasa Ikonikov, using the theory of operands, and described restricted Lie algebra as a gamma Lie algebras. And we have comparison maps between Quillen cohomology for P algebras and Quillen cohomology for gamma P algebras. So there are comparison maps. I would like to study more on this. And also the thing that you mentioned, I haven't, maybe there is an application, but I haven't done anything on that because I don't know so much on algebraic groups. But yes, it would be interesting to see that. What I know that we can construct comparisons between the Quillen-Barr-Beck cohomology for Lie algebras and Quillen-Barr-Beck cohomology for restricted Lie algebras, and even in the more general context using the theory of operands. Now, I don't know more on that. But thank you very much for this comment.
Okay. Further questions? Okay, so if this is not the case, we can thank Ioannis again.
Thank you very much for inviting me. It was a big pleasure for me. Thank you. So, bye.